So we are back again talking about infinite series, and we have learnt in the last class that you have sequence of positive terms and what is the meaning of a sum and all those things. Suppose just I have an infinite series now. AK, which is nothing but A1 plus A2 plus an plus, and it goes on, and it doesn't, there is no sign on A1, A2, an, there could be as positive numbers, negative numbers, anything. So in this case, how do I find the sum? The answer is same. You again form the nth partial sum, the sequence of partial sum. Here again it is the same thing, and then try to see whether this limit exists. So whatever be your series, it does not matter whether it have a positive term or negative term, you can have the same thing. Now once you have a series like this which can have positive term and negative term, how can I use my previous discussions that we had heard in the last class to actually make any good conclusions about this, about the convergence of this? So this leads us to the notion of absolute convergence. So absolute convergence is in the following. So you have the series as above. Now what we do ask is the following. So you know that each of AK is less than equal to modulus of AK. So then we try to look at this particular series. Now this is a series of non-negative terms, or positive terms if you want to call it, and now we know how to find the sum of that, and we know everything, some fact about this one from yesterday's class. Now suppose this converges. So here for any nth partial sum, so we had considered this series, and of course this means, so if this series converges, that is, this is some number as a sum, then this series will also converge and will have a sum, because it can't just blow up, right. So this is very important. So when if once given a series like this, if this series converges, then we say that the series is absolutely convergent. So the question would be, is there a series which is convergent but not absolutely convergent? And we will go back to answering this question. So is there a series which is convergent but yet not absolutely convergent? So we will go back to ask this question and let us see what we can do here. But before we do so, we will take a small digression, because we are taking a journey, so we can take a little bit of rest in the restaurant type of thing. Like when you travel by highways nowadays, you just sometimes stop and take a cup of tea. So it's like we are having a cup of tea now basically. So we are going to now say, is there any test by which you can know if a series is convergent? How do you know if a series is convergent? This is something very important. First of all, let me tell you, there is a simple necessary condition, there is a particular behavior. Any series which converges will have a particular behavior, right. So if you take a series of positive terms, say, so take summation AK and Ak is strictly greater than equal to 0 for all k, and if this converges, then it implies that the sequence Ak, this sequence Ak will go to 0, will converge to 0 as k tends to infinity. So, proving this is not a very big issue. Why? Because what is the sum? The sum is nothing but the, so sum S is nothing but the limit right, this is the sum. So, if you have a sequence of positive terms, this is going to happen. So, we are trying to find the necessary criteria. So, limit of Sn is S, okay. So, S is a Cauchy sequence, Sn is a Cauchy sequence, what we have learnt earlier. So, this would imply that given epsilon greater than 0, there exists n naught such that for all m bigger than equal to n naught, mod of S or all n bigger than n naught, mod of Sn plus 1 minus Sn must be strictly less than epsilon. Because this is just we are writing, instead of Cauchy sequence we are writing this particular thing, it will be a Cauchy sequence, so this will also be true. So, which simply means that what is this difference? This is nothing but an plus 1, which simply shows that the sequence an or the sequence ak actually goes to 0. So, given an epsilon, I have found an n such that an minus 1 minus 0 is strictly less than epsilon. So, this condition is just necessary, it is not sufficient. If you have a series of positive terms whose sequence actually goes to 0, that whose sequence, that is the sequence ak goes to 0, that does not mean that the sequence converges, and one of the most important example is the harmonic sequence series. So, you have the harmonic series which is given by this famous one, summation 1 by n. But if you look at the sequence ak, what is this? Or what limit of 1 by n is 0, but this sequence we have proved in the last class that this sequence does not really converge. Okay. Now, we have to find some other tests of checking when a series is convergent, which may or may not have non-negative term, or general series is convergent. So, here we will have two types of tests called the ratio test and the root test, and we will see what is the meaning of ratio test and the root test. To introduce what is called the ratio test and the root test, we introduce the two notions from sequences. One is called the limit supremum and one is called the limit infimum. So, limit infimum so it is written as liminf and limit supremum. So, these are the symbols. So, we will see what does this mean. Now, you know, given a sequence, it does not always mean that it is convergent. It could be a bounded sequence, still it is not a convergent sequence. Now, we know from the Bolzano-Weierstrass theorem, which we have already mentioned, that the bounded sequence has a convergent subsequence. Every bounded sequence has a convergent subsequence. So, we know that there need not necessarily be just one subsequence, there can be more than one subsequence, there can be infinite number of such subsequences, countably infinite of course, such subsequences. Now, each of the subsequence converges and converges to some number. Now collect all those numbers which are called the limit points of the set of the sequence and take the supremum of the limit points which is the limit infimum, and take the infimum of the limit points which is the set of limit points which is called the limit infimum. But there is a particularly interesting way to actually go ahead and define this thing. Let us see what happens. So, let us see what is the meaning of limit supremum and limit infimum, right. Okay. So, we will not get into too much of details, but we will tell you exactly what way we can work it out. The behavior of limit supremum and limit infimum is similar to the behavior of supremum and infimum. Now, so you take, let me define what is limit infimum. Here, let me take this sequence xn. Just for the heck of it, assume that it is a bounded sequence. Just for the heck of it, assume that it is a bounded sequence. It is bounded below, that the infimum exists. So, what I do first, I find the infimum over the whole sequence and I call that alpha 1. Now, I cut x1 from this one and I have x2, x3, x4, x5, x6. So, now I have technically it would look like a smaller sequence, but countably it is not, it is the same cardinality as the number line. That is exactly what we have learned. Now, the sequence, remaining part of the sequence is x2, x3 dot 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 dot. Now, if I want to find the infimum over that, the infimum is now one element has been thrown in which could have been actually the infimum, right. So, the infimum could either remain the same or it would increase. For example, if x1 is not there, so some bigger value than, if suppose x1 was the infimum, alpha 1 was x1, then some bigger value of, so among x2, x3 somebody should now become infimum because x1 is no longer there. So, then in that case it will strictly be bigger than alpha 1. So, it is alpha 2 and then I can cut off x2 and I proceed alpha 3. So, when I cut off x1 I have alpha 1, when I do not cut off anything I have alpha 1, when I cut off x1 I have alpha 2, when the sequence starts from 2. So, when the sequence starts from k, that is I have cut off all the things up to xk minus 1, then I have alpha k and so forth. So, what I have done, I have created a sequence of numbers which are themselves increasing or non-decreasing. Now, suppose this is bounded above. So, it is an increasing sequence and it is bounded above. So, if the sequence alpha k is bounded above, it implies that limit alpha k is equal to that bound supremum. So, let us call it say alpha naught. And then in this case I will say that limit infimum of xn as n tends to infinity is equal to alpha naught. So, what operation I have actually done? I have done the following operation. What I have done, I have taken infimum of x n, infimum of x n, where n is greater than or equal to k. So, it starts from k and above. So you take basically what you do, or you start with when you start with a better way to write it, for example, sorry, I am making a mistake. So I have the sequence xk exactly k greater than or equal to n. I will always like to write limit n tends to infinity, because I have written n tends to infinity. So what I do, so k is greater than or equal to n. So these are sequence which starts from xn plus 1, xn plus 2 dot goes off. So up to xn minus 1 I have removed. So I have got an infimum of that. So basically what I am doing, starting from n equal to 1, so k greater than or equal to 1, so x1, x2 dot xn. So again k equal to 2, and it goes on. So n equal to 2, n equal to 3, n equal to 4. So you will get all those things. So start with n equal to 1, then do n equal to 2, then equal to n equal to 3. Basically you are finding alpha 1, alpha 2, alpha 3, and then at the end you are taking the limit. Of course you are taking the supremum, but okay, you are essentially now you are taking the limit of this sequence, new sequence, that is n tends to infinity. So this is exactly your limit infimum. Now suppose this is not bounded below, the infimum is minus infinity, then it does not matter, then alpha 1 would be minus infinity, alpha 2 would be minus infinity, alpha 3 would be minus infinity, alpha k would be minus infinity. So if xn is not bounded below, I am writing short BDD for bounded below, it would imply what? It would imply that so now everything will be minus infinity, minus infinity, minus infinity, the limit is minus infinity. So such a thing cannot be bound, you just cannot say this has a bound, it is just all are same. So limit n tends to infinity, n tends to infinity, xn is equal to what? Is equal to minus infinity. Suppose this is bounded below, so I am not writing it clearly, I should write equal to minus infinity. Suppose this is bounded below, so you have alpha 1, alpha 2, alpha 3, alpha k, but this alpha 1, alpha 2, alpha 3, alpha k is unbounded, it does not matter. Then my limit infimum again won't be finite, it will be plus infinity. So if alpha n is not bounded above, then limit infimum xn n tends to infinity is equal to plus infinity. So it can take plus infinity, minus infinity values, and also it can take finite value. So all these are allowed in this case. See, you have to understand this fact that when I do limit supremum, it is the opposite thing, that I will do the same operation. First I will take it for the whole set, then I will do it for, so alpha 1. So if I cut off x1, then alpha 1, the next alpha 2 would be less than or equal to alpha 1, because now we have removed one element that could itself be the supremum, right. And so what you get, you will get a decreasing sequence or non-increasing sequence, and if that is bounded below, it will go and hit the infimum in the limit. So limit supremum is the following. Sorry, limit supremum xn is equal to, so first take the supremum k greater than or equal to n xk, and then take the limit as n tends to infinity. That is what is limit supremum. So basically you do this fact, maybe you can write this in a much more, if you want to be more cautious, so write this in a much more cautious. So you can describe all these things that I have written about limit infimum for limit supremum. So, this limit infimum and limit supremum business is actually used to really check whether a thing is convergent or divergent, right. So, let us just check this out. Let us now write down the ratio test and the root test for checking the convergence and divergence of the series. We are not going to prove how this will actually tell you, but this will just mention you the rules here because we really do not have time. So, we mention the rules how the thing occurs, and after that we will end with a very interesting result called Leibniz's alternating series theorem, and you will see there will be some interesting insights from that. So, this is a ratio test. So, you have a series, right. So, you really have to now check whether this sequence is convergent or divergent. How do you check it? So, what does the ratio test does? Ratio test, which is essentially due to Cauchy, all of these, is the following. Now, if AK is not equal to 0, of course, it can be it has to be non-zero. If it is a positive thing, of course, it is much more simpler then. If AK is not equal to 0 for every k, for all k, then number 1, you take the lim for lim sup. I am just giving you the information from the book of Peter Duren, which I mentioned about in the last class. Limit infimum of, limit supremum, I guess it's limit supremum n tends to k tends to infinity of mod ak plus 1 by ak. So, if this two things we will write, and lim inf of this would be strictly greater than 1. Suppose we have these things. So, if lim sup this thing, if this happens, then it implies that summation AK is convergent. So, it will have a sum, and it implies in this case that summation AK, k is equal to 1 to infinity, is divergent. Now, you can ask me a very crucial question. What if that lim sup is equal to lim sup? See, when limit exists here, when limit exists in a sequence, then lim sup is equal to the lim inf, they are the same. So, suppose limit exists and lim sup equal to lim inf equal to 1, then what will happen? Then this is slight dicey. When n equal to 1, then we can't say anything about it, no conclusion actually. So, this test would be useless, we can't do anything about it. Similarly, there is a root test. Root test is the following. There are two conditions: lim sup kth root of ak, ak to the power 1 by k as k goes to infinity, and lim inf kth root of ak, k goes to infinity. And this is strictly less than 1, this is strictly greater than 1, same story, the story is the same. So, this implies convergence and this implies divergence, but if it is equal to 1 we really do not know, this is called the Cauchy's root test. So, we have mentioned you two basic tests which you can check out on several you can just I will ask my TS to give some examples of this using the root test and ratio test to put on the your board, question board. Now, I want to end today's discussion with a very interesting result called Leibniz theorem on alternating series. Alternating series means all the odd terms, it is A1 minus A2 plus A3 minus A4. So, all the odd indices will have a plus in front of them and the even subscript will have minus in front of them. So, here is a very famous result called, so if you want to, okay, I just give you a short say a example. So, you take the sequence say minus 1 plus 1 minus 1 plus 1 and so on. So, what is the lim sup of xn here? It is plus 1 and lim inf xn n tends to infinity is minus 1. So, if lim sup and lim inf are different, you will immediately know that these are not, this is not a convergent series. So, if limit exists they would be same. So, let me write down now Leibniz's theorem for the alternating series. So, what is an alternating series? Let me write down alternating series. The proof will be on the board. This proof will not be told in the class, we hardly have time now. So, alternating series is a series like this, summation k is equal to 1 to infinity minus 1 to the power k plus 1 ak. So, it will become a1 minus a2 plus a3 minus a4 and so on and so forth. Now, what is the Leibniz theorem say? Leibniz theorem says that suppose A1 is greater than A2, A2 is greater than A3 and so on, AK is greater than AK plus 1 and finally and all the terms are greater than or equal to 0. Suppose this happen and also that limit of AK and limit of AK as k tends to infinity is 0, then summation k is equal to 1 to infinity minus 1 to the power k plus 1 AK converges. There is a crux, these sort of things are called conditionally convergent, they may not be absolutely convergent. Now, I will show you for example. Now, consider the numbers A1 is say 1, so this then half. So, consider this series, alternating series which is 1 minus half plus 1/3 minus 1/4 plus 1/5. So, now here we have that sequence 1 minus half plus 1/3 minus 1/4 plus 1, it is an alternating series just like that. And also it has all the conditions that is required for Leibniz theorem, A1 that is 1, A2 is half, A3 is 3, so A1 is greater than A2 is greater than A3 and all the things A1, A2, A3 these are all non-negative. And limit of AK, obviously limit of 1 by n is going to 0 as n tends to infinity. So, this sequence is convergent. So, 1 minus half plus 1/3 minus 1/4 plus is convergent, it has a sum. But it is not absolutely convergent, because if you look, take the modulus, then if you take the modulus of this, then the series summation mod AK would become this one, which is a harmonic series, and you know that this is divergent. But you know what the interesting part is, do you know what is the sum of this series? You will be fascinated to know this, and there are obviously lot more mathematics to be done to actually figure out what is the sum of this series. The sum of the series is logarithm of 2, and with this fascinating result, I end my discussion here. Thank you very much.